So in this second part of our notes, we're going to be looking at how to change scientific notation back into standard form, kind of the opposite of what we were just working on. So our first step is to use the exponent to determine how many places we're going to need to move our decimal. So if you focus in on our exponent right here, we have 10 to the positive fourth. That means we're going to be moving the decimal 4 spaces. For a positive exponent on 10, we're going to move the decimal that many spaces to the right. Then you'll fill in any empty loops with 0. So if we're starting with 5.34, our exponent 10 to the fourth tells us we're moving our decimal 4 places to the right, so we start it at the 5 and we go 1, 2, 3, 4 spaces to the right. It's going to land here. We fill in any extra empty loops with zeros. That means that we made the number 53,400. And that's our new number. So right below we have write each of the following in standard form. This first example says 1.8 times 10 to the first power. This is a positive exponent, so we're moving to the right, and we're only going to need to move it one time. That means it's going to land right here. We don't have any empty loops to fill in, so the number that we've made is 18, and that's our final answer. The next one, 5.42 times 10 to the positive 6th power. So again, we're moving to the right and we're going to move it 6 times. 1, 2, 3, 4, 5, 6 spaces. Our new decimal point is here. We fill in all of these empty loops with zeros. So we've made the number 5,420,000. And that's our answer. So go ahead and pause the video and try the next 4 examples on your own. And when you're ready to check your work, press play. Alright, hopefully you've tried these on your own. We have 6.8 times 10 to the third in our next example. Our positive exponent of a 3 tells us to move our decimal 3 spaces to the right. We fill in all of our empty loops with zeros, so we've made 6,800 as our number here. Our next example says 2.72 times 10 to the 9th. That means we're moving 9 spaces to the right. 3, 4, 5, 6, 7, 8, 9. We put our decimal here. That means we fill in all of our extra loops here with zeros. And if we rewrite that number without the loops, that looks right. We put our commas in to see what number we've made. We have 2,720,000,000 as our number there. So that made a really big number with that larger exponent there. Next example, we have 1.3 times 10 to the 0. So our exponent is supposed to tell us how many spaces to move our decimal, but 0 means we're not going to move it at all, so it just stays 1.3. Another way to look at that is remember that 10 to the 0 power, or any number to the 0 power, just means 1. So really we could rewrite this as 1.3 times 1. Anything times 1 is just itself, so 1.3 again. In this last example, we have 4.08 times 10 to the 7th power, so we're moving our decimal 7 spaces to the right, 3, 4, 5, 6, 7. Fill in your decimal and fill in any empty loops with zeros, and we get 40,800,000 as that number there. So hopefully you got those all right on your own. So we've done a lot of examples with positive exponents on our powers of 10, but now we're going to be talking about when we write numbers of small value, and that means numbers that are between 0 and 1. We'll be using scientific notation with negative exponents. So you can relate this back to when we talked about the positive and negative powers of 10. Whenever we saw negative powers of 10, we made numbers that were between 0 and 1. So these numbers that are represented are positive, and they're between 0 and 1. So even though they have that negative exponent, we don't have a negative number. So the next set of problems says decide if the following number will have a positive or negative exponent if written in scientific notation. So if we want to take these numbers out of standard form and write them in scientific notation, based on their value, we need to decide if they're going to have a positive or negative exponent. So this first number we have is 57 million. I'd say that's a pretty big number. It's way bigger than 1, so we're going to be using a positive exponent for this one. And that's all I want you to do here. The next one, we have 0.0049 or 49 thousandths. This number is between 0 and 1, so this is going to be a small value number, which means we'll be using a negative exponent for this one if we were going to write it in scientific notation. Try the other two on your own and then press play when you're ready. All right, hopefully you got for this one, we have 59 hundredths. That's a number that's between 0 and 1, so again, that'll use a negative exponent. Whereas our last example is 697,000. That's well over 1, which means we'll need a positive exponent for our power of 10 in this number. For the rest of these examples, we'll actually be writing them in scientific notation. So our first step is going to be to find that first digit. Remember, our first non-zero digit that is from reading from left to right. So when we look at 0.0125, reading from left to right, the first non-zero digit that we have is this 1, which means we're going to put our decimal right here. So that means our number is going to be 1.25. Remember, that first number needs to be between 1 and 10. Then we always write times 10 to some power. We're going to count and see how many loops did it take. We needed to move 2 spaces. But our last decision is, okay, was this a small number or a large number? This number was less than 1. It was not greater than 1, which means we are going to need a negative exponent. So 1.25 times 10 to the negative power here is going to give us our final answer to write this number in scientific notation. Moving to the next example, we want to make 7.8, or we're going to make 7.8 our number between 1 and 10 because 7 is our first non-zero digit. So we have to move our decimal 1, 2, 3, 4, 5 spaces. The number that we made was 7.8. We multiplied by 10 to some power. We said it was 5 spaces, but since this was a really small number, this number was between 0 and 1, that tells us that we need a negative exponent here. So go ahead and pause the video and try the other 4 examples on your own, and then press play when you're ready to check your work. All right, hopefully you've tried these on your own now. Our next example, we had 0.00058. Reading from left to right, our first non-zero digit is 5, so the number I'm going to make between 1 and 10 is 5.8. I'm going to multiply by 10. We have 1, 2, 3, 4 spaces that our decimal moved, but this number was between 0 and 1. That means we are using a negative exponent, so 5.8 times 10 to the negative 4th is our answer here. In our next problem, reading from left to right, our first non-zero digit is 3, so the number that we make is 3.14, and our decimal would have started at the end here, 31,400. If that was in dollars, remember our decimal's all the way to the right. We have to move our decimal 4 spaces in this case, so we're writing times 10 to the 4th power, and then go back and consider, do we need a positive or negative exponent? We started with 31,400. That number is greater than 1, so we will be using a positive exponent on this one. Moving to our next example, we have 4,300. Our first non-zero digit is 4, so we're going to be making 4.3. The decimal would have started all the way to the right here, which means it's only moving 3 spaces. So when we multiply by 10, we're going to have an exponent of 3. 4,300 is greater than 1, so we do need a positive exponent, so 4.3 times 10 to the 3rd is our final answer on this example. Our last example here is 0.00026. Reading from left to right, our first non-zero digit is 2, so 2.6 becomes our number between 1 and 10. That takes us 1, 2, 3, 4 loops to get there. So we're multiplying by 10 to the 4th. However, we started with a number that was between 0 and 1, which means we needed a negative sign on that exponent. So 2.6 times 10 to the negative 4th is our final answer in that example. So looking down at the bottom of your paper, we have just a note about when we change numbers from scientific to standard form. We have to consider we have a decimal times 10, and then there's always going to be some power up here. If that power, that exponent, is negative, we move our decimal to the left. But if that exponent is positive, then we will move the decimal to the right. It's just like whenever we talk about negative and positive numbers are always to the left of 0, and positive numbers are always to the right of 0. So that can help you remember that. So we have our last set of examples here. We want to change these numbers that are written in scientific notation into standard form. So in our first example, we have 8 times 10 to the negative third. So we're starting with an 8, and the decimal on 8 would start here. Think about if we had $8, it would always be to the right. We're multiplying by 10 to the negative third power. We talked about negative exponents mean we go left, and positive exponents mean we go to the right. So in this case, we'll be moving our decimal 3 spaces to the left. So we count 1, 2, 3. To the left, our decimal is now here, and remember we fill in those empty loops with zeros. So the number that we've made is 0.008 or 8 thousandths. So double check your answer makes sense at the end. We started with a negative exponent and we got a number that's between 0 and 1, so those make sense. If you had accidentally gone to the right, you would have ended up with 8,000, and then we would have looked back and said, oh, well, I had a negative exponent, so 8,000 doesn't quite make sense there. On our next example, we have 9.3 times 10 to the 6th. We have a positive exponent this time, which means we move 6 spaces to the right. 1, 2, 3, 4, 5, 6 spaces to the right. Fill in all of your loops with those zeros, and we get 9,300,000 as our final answer. That number is definitely greater than 1, and we did start with a positive exponent, so that does make sense. Go ahead and pause the video, try these last 4 examples on your own, pay attention to those negative and positive exponents. Okay, hopefully you've tried this on your own. In this first example that I asked you to try, I have 1.8 times 10 to the 5th. 5th is the positive power, so we're moving 5 spaces to the right, which means we'll add in our zeros and our loops, and we get 180,000. That's a number greater than 1, and we had a positive exponent, so that matches. That looks good. In our next example, we had 5.04 times 10 to the negative 5th. So negative numbers for our exponent, we move to the left. So we're moving our decimal 5 spaces to the left, and we fill in those empty loops with zeros. That means that we get 0.0000504. This is a very small number. It's between 0 and 1, and we started with a negative exponent, so again, that makes sense. Bottom 2 examples, here we have 6.8 times 10 to the negative 7th. Negative exponents, we move to the left. 1, 2, 3, 4, 5, 6, 7. We fill in, we put our decimal, and we fill in all those empty loops with zeros, so we get 0.0000068. That is a number that is between 0 and 1. We started with a negative exponent, so that does make sense. Our very last example, 2.72 times 10 to the 9th power. We have a positive exponent again, so we're moving to the right. That's 9 spaces. We put our new decimal, fill in all of those empty spaces with zeros. So we get 272, 4, 7. We are getting 2,720,000,000, and that is a very large number, greater than 1, and we did start with a positive exponent, so again, that makes sense. So just keep in mind when you do all these problems, go back and check your work at the end and make sure that the exponent that you started with makes sense with the number that you end up with.